Okay, so now we're going to do the same thing that we did in the last video for arc length, but in 2 dimensions, so we're doing it for surface area. So in particular, I'm going to start by looking at just some generic parameterized surface in R3. And so we'll suppose this is parameterized by the variables u and v. And we'll take some little patch, let's take it a rectangle just to make it so it's not too horrendously complicated. Okay, so we've got this, and so this is going to be our domain D, and then we're going to have our parameterization, which we'll again call R, which, by the way, is the dumbest letter ever for this. I actually like this book quite a lot, but I will never forgive them for using R for both a curve and a surface, especially when it can be confused with radius and directly conflicts with it on many accounts. Okay, end of rant. In most other regards, I quite like the book. Okay, so let's see. So let's draw some kind of cool surface that this thing is mapping out here. So we've got some kind of thing looking like that. Okay. So there's like some piece of a torus or something like that, right? Looks cool, yeah. Okay, just to show you how these match up, let's say that like this edge along here gets mapped to this curve right here, and this edge over here gets mapped to this curve at the other end, and so you can see how it's like, you know, took some rug and kind of rolled it up and smeared it around, whatever. Okay, so now if we are at some point, say this point right here, so that would be like maybe over here somewhere. The embedded image of it would be. Then, and this by the way that's S, my surface. Then that little patch right here is going to get mapped into some little patch over there. And let's say we're doing like if we move a little bit in the U direction right here, then we can see going that way is going to be the partial of R with respect to U. And if we go a little bit in the positive V direction over here, then that's going to be in the well, it's a little shaky there. That's going to be RV, the partial derivative going that direction. And then there's going to be this little sort of patch of area here mapped. So what I'm trying to draw kind of like a little piece of the tangent plane that attaches to this green dot at this particular point of the surface. And I want to point out to you that on an infinitesimal scale, that little tangent plane is spanned by the vectors RU and RV, which are the partial derivatives of the embedding, the parameterization R. And so here we've got that R of U and V, it has several coordinates. It has a X coordinate and a Y coordinate and a Z coordinate, right? And this is for UV in D, our parameter domain, that little blue rectangle there. And the area here is going to be the magnitude of RU cross RV. Remember, that's one of the properties of the cross product is that the magnitude of the cross product vector is the area of the parallelogram spanned by those. And so we can work out RU cross RV from the usual determinant definition of the cross product. In case it's been a while, let me write it down for you. So we've got IJK across the top, and then that's right. XU, YU, ZU, and then we've got XV, YV, ZV going across the bottom. And that's how we come up with our new vector. Now I'm not going to work out the components right there, because because we don't need that yet, but we do have our area element, which the book also calls GR, which, like I said, is dumb, but oh well. And that's going to be the magnitude of RU cross RV times dA, our area element. And then here, dA, that would be du dv or dv du, depending on how you want to set it up. Okay, so far so good. Now that tells us what an infinitesimal patch of area looks like. So if we take these together over the entire surface, the area of that entire surface is going to be the double integral over S, the surface, of dr, which, given a parameterization, so a formula for our parameterization R, would be the double integral over d of magnitude RU cross RV, the area. Okay, so there's a bunch of nonsense symbols that, you know, mean something, but who cares, right? The important thing that we're looking at is the special case when S is the graph of some function, let's call it z is equal to a function of x and y. Then, just like before, we can actually parameterize by the independent variables. So we can take u to be x and v to be y, and it'll work for a parameterization. And then to ensure that we are on the graph of the function, we need to be, when we're at x and y, we need to be at the height f of xy. So that parameterizes our surface as x and y range over the domain of f. Okay, so we also have now that if we look at Rx cross Ry, this is going to be given by the simpler ijk, and then derivative of x with respect to x is 1, and with respect to y is 0, and then we have the partial f sub x. And then we have 0, 1, and f sub y for the partials of y on the third row. And so when we work this out, let's see. So for our first coordinate, we're going to be looking at the subdeterminant right here. So that's going to be 0 minus f of x. And then for the next one, we're going to be looking at the jth coordinate. So it's going to be 1 times f of y minus 0 times f of x. So in other words, f of y. Except now we're in the second coordinate, so we get a minus sign. And then for the third one, we are looking, so for the third coordinate, we're looking at the subdeterminant 1 minus 0. Okay, so there you have it. That's our cross product. And that implies then that the magnitude is going to be square root of the x partial squared plus the y partial squared plus 1 squared, which is 1. And we have our area element. So now if I want to figure out what the area of this surface is, I just have to take the double integral of this sucker and that will give me the area of the graph of f, or the surface area of the graph of f.